If body fat is such a heavy contributor to insulin resistance, how does it cause it? I just want to go through a brief primer on that, just to help you better understand the purpose of the rest of the talk. Within the realm of fat cells in the body, as fat mass is growing, it's actually growing usually through one of two ways, and in some instances, both. And so one of two ways. The first one being hypertrophy of each individual fat cell, and the second being hyperplasia, which is when the fat cell size is staying generally the same, but the fat cells multiply to help share the metabolic burden. So hypertrophy is when the number of fat cells is generally quite set, it's static, but each fat cell is bearing that burden, and it's getting bigger and bigger. In contrast, hyperplasia, if fat tissue is being stimulated to grow, it will maybe get modestly bigger, and then it will multiply. And so it starts to recruit help to carry the load. There are two problems with hypertrophic fat gain. The first one, and both of these are actually quite complicated ideas, but I'm hoping that I can convey them in the simplest possible way. So the first problem with the hypertrophic fat cell is that it starts to run out of room. It's essentially like a metabolic hotel that has no vacancy. Now, let's come back, let's leave that analogy behind for just a moment and come right back to the fat cell. So insulin stimulates adipocyte, which is fat cell growth. It largely does this, and we'll revisit this in a moment, by inhibiting the breakdown of fat with a generally modest influence of pushing in more fat. So that making the fat cell grow, inhibiting the breakdown. But when the fat cell is undergoing such substantial hypertrophy, it begins to reach a point of maximum dimension. It's like a water balloon that we've filled so much that if we put any more in, it's going to pop. Now, in this case, it's like a water balloon where we can't totally turn off the faucet. And so rather than have the water balloon pop, we just make one teeny little hole and allow it to start leaking out. That's what starts to happen in the hypertrophic fat cell. It becomes resistant to insulin's efforts to force it to hold on to the fat in order to prevent further growth. So it's a survival mechanism. So the hypertrophic fat cell tells insulin, you want me to continue to grow? I can't. I will literally pop because a membrane has a limited capacity to continue to grow, like a water balloon has a limited capacity to continue to fill. And so the fat cell becomes insulin resistant to prevent further growth. Now, the second problem with hypertrophic adipocytes is that they start to suffocate. Or to use a more cellular term, they begin to experience hypoxia. Now, it's a little known fact of cell biology that a cell must be within just a few microns of a capillary. And a capillary is the smallest functional unit of a blood vessel, of a cardiovascular system. It is at the capillaries where we exchange stuff with cells and tissues. That's where we're giving out oxygen, taking in CO2 into the blood, giving nutrients, taking in metabolites. It only happens at the capillary, not the arteries before it, not the veins after it, or any of the smaller structures in between, only the capillaries. So a cell must be very, very close to a capillary to allow all of this exchange to continue to survive, including getting oxygen. Now, if you have small fat cells, that's no problem, like I show at the bottom. They're well within this generally 50 micron range of the distance of the capillary. However, fat cells are so completely unique compared to other cell types, it can expand to more than 10 times its volume as it starts to undergo hypertrophy. Now you have a fat cell whose very diameter is so substantial that it puts even itself, let alone any neighboring fat cell, much too far from the capillary. So now you have capillaries whose distance is too great, or fat cells, hypertrophic fat cells, whose distance is too great. As they've undergone hypertrophy, they've pushed themselves further and further from the capillary, from the life-giving blood. And now they've become hypoxic. They're suffocating. And the fat cell, however, wants to survive, and it has so many tricks. The fat cells are so complicated. We look at them as just energy storage, and they do so much more than that, including sensing hypoxia and responding to that hypoxia by releasing pro-inflammatory cytokines. So the hypertrophic fat cell will say, I'm suffocating. I need to correct this by stimulating the growth of new blood vessels. And I'm going to do this by flooding the system with pro-inflammatory proteins, because some of them will in fact induce the growth of new vessels, thereby correcting the hypoxia. Now, unfortunately, these two things that the hypertrophic fat cells do to survive end up creating so much of the metabolic mayhem that we see throughout the rest of the body. So the rest of the body is just suffering as an innocent bystander, all while the fat cell is just trying to survive. All right, now with all of this in mind and your appreciation, I hope, of the problems of the hypertrophy of fat tissue, let me just sort of go on a brief tangent and allow this, let this be a vehicle to introduce an interesting theoretical concept known as the personal fat threshold. You've probably heard of this. This was an idea posited many, many years ago, that within certain bodies, people will have a varying threshold above which that body doesn't want to store more fat. Now, you'll have to pardon my excessively cartoonish method. It's not to say that anyone who has fat stored above their nipples is going to be metabolically deranged. I just mean to show that this would be a level in a particular body that once that body has reached that degree, maybe as a % of fat, then it's going to start to suffer. So any fat mass or amount of fat stored in fat cells that is below that threshold, it hasn't met the threshold, we would say this person is insulin sensitive. They are not suffering any metabolic complications from the amount of fat that they have on their body. However, if a person has gained a certain amount of fat or stored a certain amount of fat within their adipose tissue or their adipocytes that has gone beyond the optimal storage, or it's pushing it, now they start to move into the realm of metabolic derangement in the form of insulin resistance. And what if you could take this person that I'm showing here who has insulin resistance because they have overfilled their fat cells and make their fat cells go through hyperplasia? You'd think if the story I just told you is true, that filling fat cells is what creates not the total amount of fat on the body, not the fat mass, but the size of each individual fat cell. If those fat cells have gotten big, they have insulin resistance. If you could go to that fat tissue and make it undergo hyperplasia, you would have a paradox occur metabolically, because you have on one hand expanded their ability to gain more fat, but what do you think happens to now their fat threshold? Even though they've gained more fat and their threshold was here, they went beyond it. By forcing them to gain more fat through hyperplasia, you push up the threshold even higher. So even though they're fatter, this is the paradox, they're now in fact insulin sensitive. This is actually the mechanism of action of a class of anti-diabetic medications called thiazolidinediones, or TZDs. They improve insulin sensitivity by increasing a patient's ability to store fat by activating hyperplasia. Isn't that fascinating? It's a hell of a drug. And usually the patient will be the one who wants to get off it because they get tired of buying a new wardrobe every 6 months. All right, so let me just show another instance of the relevance of this before we move on to the actual growing and shrinking of the fat cell. This was a paper that was published that explored in people who were controlled for % body fat, BMI, age, sex, etc., of a Caucasian population and a South Asian, sometimes referred to as Indian. So South Asian and Caucasian. Same % body fat, same fat mass. And they did fat biopsies like we do in my lab and measured the size of each of the fat cells. Look at the difference in fat cell size between the Caucasian fat, if you will, or the fat on the Caucasian body versus the fat stored in the South Asian body. You can see the fat stored in the South Asian body is substantially more hypertrophic, despite having the same overall body fat mass. So based on this, who would you think has the higher threshold? Who could store more fat, in other words, and yet maintain their insulin sensitivity and their metabolic health? Remember, fat cells are healthier cells. So it's no surprise that the Caucasian population has a higher threshold. Thus, if you take an equal amount of body fat across the population, you will see that one group will have surpassed its threshold and thus be insulin resistant, while the other is still doing metabolically fine. This partly explains some of this odd paradox we see a little bit. I'm using that word too much. What's another word I can use? This disconnect that we see from the US to, say, India, where within the United States, we have much, much higher levels of obesity. But if you look at diabetes, India has higher rates of type 2 diabetes, despite being leaner than the average American, with being such a heavy Caucasian population. All right, so one last thought on this, though, before I leave it, is who do you think would have the higher insulin levels? You've heard me speak by now, I'm sure, and you're all such diligent students that you've remembered it. If someone is insulin resistant, what happens to their insulin levels? Always. Insulin will be higher. Yeah, so who do you think is going to have the higher insulin here? It's going to be the group that has the more hypertrophic fat cells or the lower fat threshold. So the average Caucasian has a fasting insulin of around 9, and the average South Asian has a level that's about double that. So the growth of a fat cell, and this is a guy who's growing fat cells in his lab all the time. And then we're taking fat cells from animals. We're taking fat cells from humans. So I want you to appreciate this experience and my knowledge on the topic, because I know that people debate it, and you hear all kinds of sources of what makes fat cells grow and shrink. If anything you've heard disagrees with what I'm about to say, they're wrong. Anyway, so what makes a fat cell grow? Well, you need two things, and you really do need two things, as much as they've been split into two different camps. You need elevated insulin, and you need sufficient energy. These are not the same, but they work together. Insulin provides the necessary, utterly essential signal to the fat cell to grow. But in the absence of fuel, the fat cell will say, well, I'm trying to grow, but I have nothing to grow with. You must have sufficient energy to fuel the growth that the insulin is stimulating. You truly cannot have fat cell growth with one but not the other. And we're going to go into that in more detail just so to explore what happens when we start manipulating the arrows a little bit. But let's just start with the purely energy-based paradigm. Looking at, again, just the level of the fat cell. If you have elevated energy, you would have sufficient glucose. And fat cells love glucose, and they love turning glucose into fat, and they do so very, very well. But fat cells also have the ability to simply pull in fat. Now, I don't want my cartoon-ish image here to confuse. I don't mean to imply that the adipocyte actually directly pulls in a triglyceride molecule. That doesn't happen. But the triglyceride molecule will float by it, and then it will rip off individual fats from it. And I'll come back to that in just a moment. Now, these are the inputs. Of course, fat cells have an output, and that would happen in the form of free fatty acids. So the overall balance of these caloric molecules in versus these caloric molecules out, this could, at its simplest, be defined as the caloric theory of why fat cells grow, or the caloric theory of why we get fat. More energy is going into the fat cell than is going out. That is the simplest version of this. However, even right here, we've encountered a bit of a conundrum. If it truly is, there's just excess energy in the blood, there's calories in the blood that need to be stored, what happens then with exercise? How is this regulated? So exercise is a perfect example, because when we exercise, the amount of energy coming out of the fat cell goes up. Free fatty acids go up a lot. But so too do other energy sources in the blood, like glucose. Why isn't the fat cell picking in all of this glucose during exercise? Why isn't it getting the overall signal that it should be growing because of all this glucose that's available in the blood? And again, the fat cell loves taking in glucose to store for energy. Well, that's because even though there is plenty of energy in the blood, and indeed the fat cell is contributing to it, the fat cell knows that it's time to release fat rather than store it because of, any guesses? Yeah, hormones, specifically insulin. It is the hormone that tells a cell what to do with the energy that it has. We cannot assign a level of intelligence to a cell that it doesn't have. A cell must be told what to do. It's one of my naughty little children. It must be told, heaven forbid, the child just do what it knows it should do on its own. Like the fat cell should just know what to do with the energy. It does not. It must be told what to do, and it is told what to do based on the input and the overall energetic state of the entire body. A cell alone doesn't understand what's going on in the entire body. It's hormones that tell one cell here what's going on. This hormone is hungry. It'll be some endocrine cell that will signal to the other cell that's storing the energy, telling it that it's time to give it up, or vice versa. It's hormones that communicate the overall needs of the body from one cell to the other, lest any cell become too selfish and only care about itself. Now, let's shift then and leave this kind of energetic aspect behind of pure calories and then just discuss about the purely endocrine aspect of fat cell growth and shrinking. But let's keep these energetic inputs and outputs still superimposed on the fat cell. Insulin is relevant with the growing and shrinking of a fat cell for two reasons. The first being that it will activate the input of energy into the fat cell, and it will inhibit the output. Remember, insulin wants to tell the fat cell, there's energy here, this is what I want you to do with it, namely store it. So the first one, increasing the uptake of energy into the cell. Insulin will dramatically activate the influx of glucose into the fat cell. And then as that glucose comes in, because insulin is not only opening the doors for the intake of the glucose, but it's also activating all the enzymes, or in other words, sending the message, hey, I'm giving you glucose and I want you to turn it into fat. And so the fat cell obliges and begins turning it into fat very, very easily, very readily and rapidly. Now, what about the fat? I have, in fact, sometimes had this sort of weaponized against me, showing studies of the role of insulin in changing fat intake into the cell in the form of free fatty acids. The problem is those experimental models they're flawed, because it's not, a fat cell's not going to be pulling in free fatty acids. It's going to be taking a circulating triglyceride. Well, it does pull in a free fatty acid, but it has to pull it off the triglyceride first. And it does so through the actions of lipoprotein lipase. So lipoprotein lipase will see the circulating triglyceride, and if there's lipoprotein lipase in the blood vessels that are feeding the fat cells, it will say, hey, hold on, right as you come by, I'm going to pull in a fat from you. I'm going to rip it off. I'm going to rip off another one. I'm going to rip off another one, and just keep storing it in the fat cell. Insulin activates lipoprotein lipase. If you don't have insulin, you will not have any lipoprotein lipase within the adipose tissue that is active. And so the fat just passes you right by. It never gets pulled in. So insulin is both activating the input, and as I said a moment ago, it's also restricting the output. It is slamming the door on lipolysis, which is the technical term for the breakdown of the stored fat. This, in its simplest form, represents the endocrine theory that insulin promotes fat storage. Now, just as a simple example of this, I already mentioned to you that we're growing fat cells in my lab all the time. In fact, there's no cell that we experiment with that is harder to deal with than fat cells. It's a particular irony of science that I can grow muscle cells in my lab easy. Any one of my students learn how to do it in a day, and they're all expert at it in no time. But try to grow fat cells, isn't that ironic? That it's muscle cells that grow so easily, and it's fat cells that are so fickle and difficult. In reality, it's all our fat cells that seem to grow nonstop, and it's our muscle cells that we wish we could get more of. It's not the way in vitro. When you have cells growing in a petri dish, these fat cells are fickle. Now, what do we do with them? We have the fat cells plated. They're adhering to the bottom of the petri dish, and they are swimming in a sea of fats and glucose. They have all the energy they could want, and yet we're checking them every day, looking at them under a microscope. They are these rinky-dink, small little cells. They don't look anything like fat cells. They just look like little fibroblasts, just normal little cells, until we do one thing. Because they don't know what to do with that energy, right? Even though they're alive, they're breathing cells. They're alive, we're changing the medium, we're keeping them healthy, but they stay very small. They don't know what to do until we tell them what to do by giving them, yes, we give them this little cocktail, and if we have to have insulin in that, or they don't know what to do. The moment we spike in the insulin, we can check it even just a few hours later, and immediately we start to see the lipid droplet stimulating the growth of the fat cell. Now it's a fat cell, beyond name only. In all function and glory, it's a fat cell, just like we would expect. So you can take this statement to the bank. Fat cells cannot grow unless insulin is elevated. It is utterly and completely impossible. There is no growth of the fat cell unless insulin is elevated. You cannot make it happen. All right, now let's start to play with things a little bit. What if energy is up, but insulin is down? And let's take an individual who has excess fat that needs to be shrunk. We need to shrink these fat cells. How can fat cells shrink if energy is abundant and yet insulin is down? How could that happen? Pure thermodynamics will say it's impossible. Of course, pure thermodynamics is making all kinds of assumptions, like that the body is the universe. It's a closed... Now, I have some students who think that they're the middle of the universe, but they don't think that they're the entire universe, this closed system of the entire universe. The body is an open system that's exchanging energy in and out in ways we can't possibly fully control for. Even in the best labs, it's difficult to do this. And it's impossible in real world. Counting calories is laughable. You just cannot count them. You cannot account for them all. So what happens though? If energy is abundant, but insulin is down, how can I be so bold as to say the fat cell will still shrink? Because it will. Two things will happen. One, energy expenditure will go up by a lot. And I'm going to revisit this in just a moment. So the body literally starts running hotter. You're increasing the idle of the engine. Resting energy expenditure just goes up. And not even a little. And then second, which accounts for a lot of energy, is just this phenomenon of wasting. And I have mentioned this before in previous talks, but I'm just re-emphasizing it, bringing it back in here. Now, case in point, we can see this in humans in the case of an insulin knockout, a human insulin knockout model. Can you guess what I'm actually talking about? Type 1 diabetes? Yeah, so we use the term knockout to refer to genetic knockouts in animal models, but we have human knockouts of insulin production, which is a type 1 diabetic. This whole topic, and indeed much of my fascination on adipose tissue as a scientist, came because of this absolute serendipitous stumbling upon this work that was published over 100 years ago by two absolute legends. Elliot P. Joslin being the godfather of modern endocrinology, and Francis Benedict, whose influence on metabolic rate is still evident this day in the form of the Benedict equation, which is a way of estimating metabolic rate based on the size and mass of a person. Because metabolic rate is largely driven by just how much body there is. So a bigger person, you take one lean, if I were to gain 50 pounds, guess what would happen to my metabolic rate? It would go up, and it would go up a lot. So the bigger the body, the higher the metabolic rate. And yet what they found when these two geniuses came together, they found that in cases of what they called severe diabetes, at the time they didn't call it type 1 or type 2, it would just be type 1, that's what we would call it. They found that the metabolic rate was 20% too high. Now that's a lot. That is several hundred calories a day associated with just living their life. It's not like they're on a Stairmaster or anything all day for 3 hours to try to burn these several hundred calories. Just the very act of living their life in the absence of insulin meant that everything is happening at a higher level. Energy expenditure is just moving. Now in 1984, which is a wonderful year because that's when BYU won the national championship. So what they did here in 1984 was, first of all, they confirmed the findings of Joslin and Benedict and found that an untreated type 1 diabetes metabolic rate was way too high. Something was wrong here. They were just running too hot, if you will, the engine. And then what they did, they treated them with insulin, which is something Joslin and Benedict couldn't do because it wasn't available yet. They gave them insulin injections and noted, boom, metabolic rate went right down to normal. It went to where you would have expected it based on their body size. Interestingly, they documented this minute over minute, and this is the exact data. I just superimposed my own figure so I could maintain my obsessive aesthetic. But they found that it went down at the very minute they began treatment and continued to go down until the very ending, and it would have indeed continued to go down for hours. Just with one single insulin dose, they would slow that metabolic rate by what would end up being several hundred calories. Now, all of this, even as much as I'm talking about the energy wasting of metabolic rate, What I didn't even work into this lecture for the sake of time, although now I'm taking time talking about it, is the production and the breathing out or the urinating out of ketones. Remember, ketones have a caloric value roughly similar to glucose. And now all of a sudden, in ways that we cannot capture fully, we're breathing out ketones, we're urinating out ketones. That's another mechanism whereby if insulin is low, the body cannot store that energy. It must get rid of it. And it does so by making everything just burn more. You have a higher metabolic rate, you're producing more heat, which is waste, and you're wasting the energy, not only glucose in the urine, if it's really extreme, but just the production of ketones and emitting those ketones in the breath and in the urine. All right, now what about low energy? Let's flip this one around this time. If energy is restricted, but insulin stays high, now we've created a bit of a problem. Because here we have the individual, once again, who has fat cells that are growing or shrinking. But if there's little energy coming in, but insulin is still high, it would be forcing, and I say it would be because now we've gone into the realm of theory, and I'll show you why in a moment. It would be forcing all of the energy into the fat cells, most especially, but any of the body's cells. But again, especially fat cells. So now the fat cells are being told to grow, all while the total amount of energy in the blood is starting to go down. The fat cell doesn't care. It has plenty of energy stored. Even muscle cells don't really care. Muscle cells have a lot of energy stored as glycogen and fat. The liver's got plenty of energy. The kidneys have their own glycogen reserve. They can handle a little bit of reduction in energy in the blood. But one tissue among the trifecta of high metabolic rate organs, very high metabolic demand, doesn't store energy and must constantly be pulling in energy from the blood. But if energy in the mouth is going down, all while insulin stays elevated, which is pushing all the energy into the cells, the brain is left wondering how it's going to continue to get fed. Because if you are lowering energy in the blood, the brain isn't getting any. And so the brain starts to panic and is left with two choices. I either have to reduce my function, shut off, and reduce my energy demand, or I'm going to try to continue to work at this level and die. So it's better to go unconscious. This is essentially what happens in humans who overdose insulin, like this study with Dr. Cahill. So not only does, if there's no energy coming in and you spike insulin, glucose goes down, but then you would say, well, that's fine, Ben, because the brain has another energy source, ketones. But what happens to ketones if insulin goes up? Ketones also go down. Now you've deprived the brain of its two energy sources. No surprise that the brain shuts off. This would be known in diabetic realm, as diabetic shock. But this is why this scenario that I've outlined, namely low energy but high insulin, cannot happen. If energy is restricted, insulin must go down. Because insulin only wants to store energy. And if there's limited energy coming in, the body cannot afford for insulin to stay high. Now, therein lies the rub. Therein lies the problem with virtually every study that is comparing low-calorie to low-insulin diets. Or to say that another way, a low-fat diet, hypocaloric low-fat diet versus a low-carb diet. Now, as a reminder, and this is, once again, data that is just directly superimposed on a figure. We have done these experiments in my lab, and we're going to publish them soon. You can see that it's only carbs that have a substantial or any demonstrable effect on insulin at all. Now, those who were in Dr. Kutnick's talk this morning, you're saying, well, Ben, he showed an insulin curve. These are non-diabetic. If a person is a diabetic, they will have an exaggerated response to the protein that a non-diabetic won't have. So these are real human data. And my data from my lab is exactly like this. Although I'm not showing mine, I'm showing someone else's work here. This is for an insulin-sensitive person, non-diabetic. If it were an insulin-resistant person, the insulin spike to glucose would have gone up substantially higher and taken an hour or two longer to come back down. Just as a reminder. So we have the low-calorie, low-energy, low-fat diets versus low-carb, or in other words, low-insulin diets. And how do they compare? Now, in this case, if you're putting someone on a low-energy diet, given what I just explained to you before, if you restricted energy and you allowed insulin to stay high, that is incompatible with life and the person's unconscious or dead. So what do you think happens? If you have a low energy diet, what's going to happen to insulin in order to ensure survival? Insulin will go down. every time. So we have this massive confounding variable that has existed with every single low-calorie, low-fat diet. They say that they're testing the carbohydrate insulin model versus the energy model, or the caloric theory of obesity, whatever they would call it. But there is this enormous confounding variable that is present in every one of these low-calorie diets. Here's an example. This is maybe the most famous study. It was 2 years that looked at these 3 diets. Now, just to describe the diets, they had a low-fat and then a slightly higher fat version, what they called the Mediterranean diet, which of course means whatever you want it to mean. But interestingly, they were clamped calorie. They were calorie clamped. They said you must eat a lower calorie diet. So first of all, just think for a second. If you take the average person eating the standard American diet, or I could call it the global diet, because that's what it is, eating the standard global diet, which is about 70% carbohydrate and hypercaloric, and you force them into a low-calorie diet, they're eating less of everything. They're even eating fewer carbs than they were before. So just as a reminder at how silly this is to try to use these kinds of studies to make these comparisons. Then they had the low-carb diet, which was calorie unlimited, and it was carb restricted. Now notice that it started at 20 grams, and then partway through they increased it to 120 grams. That's a pretty substantial increase. Now, throughout this study, looking at these 3 metrics, glucose, insulin, and insulin resistance, there was a consistent loser and a consistent winner, which is nice. And this is a heavily studied or cited paper. You can look it up. Now, they also looked at weight change. I'm just showing this as an interesting example of what would be happening to the shrinking of the fat cells. The low-fat diet had some drop. No surprise, they're cutting down energy. And remember, they're also cutting down everything that they were eating before they started the study. They're eating less of everything. Mediterranean diet had slightly better results. And then coming in for the win was the low-carb diet. But boy, what a drop and what a weird increase. What do you think happened at the point of that drop? I already gave you the hint. Yeah, the scientists were concerned about the rate of weight loss. They considered it to be too much. And so they increased the carbs in order to mitigate that weight loss, lest it become a confounding variable. That's what the justification was, actually. Now, what happens to insulin to prove my point? No surprise that the low-carb diet experienced the greatest drop in insulin, insofar as carbs are the main spiker of insulin. And then the Mediterranean diet had a reduction. It was more subtle. And then still, the most subtle, but still a significant drop was in the form of the low-fat diet itself. So every one of these diets was lowering insulin, because if you just restrict the amount of food a person is eating, insulin will come down. So how can we really know that we've ever tested the endocrine theory of obesity or the caloric theory of obesity in these weight loss studies? And there's so much fervor and arguing about them when we have this massive confounding variable. So what my idea is, how can we account for the confounding variable? We need to forget about weight loss studies and look at weight gain studies. We need to put these same diets in a hypercaloric state and acknowledge the confounding variable of low energy leading to low insulin. So the reduction in insulin is going to be present among both interventional groups. So rather than just saying, how can we make someone lose the most weight, we should say, how can we see who gains the most weight? Which of these 2 diets is going to be the most resistant to weight gain, and which is going to be the most favorable to weight gain? We're flipping it all around. So we use the weight gain diet, and in this sense, I think we actually could understand the origins of obesity. After all, that's what we're trying to study, right? We're trying to understand the endocrine origins of obesity versus the caloric origins of obesity. Then why are we always using anti-obesity treatments? Why are we always doing weight loss studies? We need to do weight gain studies. And if you pay college students enough, you can get them to do anything, including gain 10 pounds or whatever it may be. Now, has this ever been done? To my knowledge, there has never been a large-scale study that has done this, and I have looked. There have been overfeeding studies before, but not that have separated into 2 groups, being low-fat versus low-carb hypercaloric. I've never seen it done except one study. It was an N of 1, which I appreciate greatly. I have long been saying we need more case studies to enter the realm of clinical research. I've long been an advocate of this. And this was a perfect example because it's literally the only one I could find. This was an interesting set of experiments done by Sam Feltham in the UK, partly influenced by Dr. Eric Westman. So Sam clamped calories with a washout period between each of the diets, and he set it to, he had to eat 5,800 calories a day. That's where he set himself. And he did a low-fat version and a low-carb version with the macros split, as I show you here. So very heavily, roughly matching the global diet. So the global diet is around 65-ish% carbs, up to 70% carb. Well, that's what he did. And the low-carb diet going really, really low-carb, but still these big calorie loads every day for, I think it was 2 weeks. And then he looked at two outcomes primarily, body weight and waist circumference, which I appreciated the waist circumference because we all know body weight is more than just body fat. So in the first case, when he was on the hypercaloric low-fat diet, he saw that his body weight went up by 7 kilos. That's pretty hefty. And on the low-carb diet, it only went up by a little over a kilo, so a pretty substantial change in weight gain. And he would always get back to baseline before he started the next round. Then he looked at waist circumference. He found that on the low-fat hypercaloric diet, his waist circumference went up by 9 centimeters. That's a nice, once again, increase. That's another couple notches in the belt. And then on the low-carb diet, his waist circumference went down by 3 centimeters compared to getting back to baseline. This is how we need to do it. If we want to understand why fat cells grow and shrink, if we're only ever forcing them to shrink, we always have the confounding variable of low insulin, because insulin is the hormone of the fed state. And if we are feeding less, it's no surprise that insulin must come down, and that will always be a confounding variable.